Alright, so in this video I'm gonna be explaining this model DICE, which is a data-efficient clinical event extraction with generative models. So this paper in 2023. Event extraction for the clinical domain is an underexplored research area. The lack of training data along with high volume of domain-specific terminologies with vague entity boundaries makes the task especially challenging. In this paper, we introduced DICE, a robust and data-efficient generative model for clinical event extraction. DICE frames event extraction as a conditional generation problem and introduces a contrastive learning objective to accurately decide the boundaries of biomedical mentions. DICE also trains an auxiliary mention identification task jointly with event extraction tasks to better identify entity mention boundaries and further introduces special markers to incorporate identified entity mentions as trigger and argument candidates for their respective tasks. So this is an illustration of sign symptom event, which is triggered by this word with multiple arguments, including an area argument and a diagnostic procedure event, whose predicate is computed tomography, described by argument chest of real biological structure. There are several non-trivial challenges of clinical EE compared to general domain event extraction. First, most triggers and arguments of clinical events consist of domain-specific terms that are more than 50% longer than the general domain on average. This is a model design of DICE, and they use T5 large as the backbone text generation model for the two joint models. The entity detection module extracts event trigger and type, and this module extracts argument and roles, but they are trained jointly with the trigger and argument modules for mentioned enhanced event extraction. So you've got the passage, and using this prompting method, we can train it jointly. The ED and MI module. So this is the statistics. So we use this data set ACE5, but here they use other data sets as well. In the metrics, for example, the average trigger word count for AC is 1. For this one is 1.61. We formulate EE as a conditional generation task so that we can incorporate domain knowledge such as event type and argument role definitions via natural language in the input prompt. To tackle the challenges of clinical EE, we further enhance the EE model's specialization in mention identification by techniques to handle long clinical mentions with vague boundaries, and perform an independent query for each event type or argument role for better long-tail performance. There are three main components: mention identification, which identifies the candidate pool of event triggers or event arguments. Then we have event detection. This component extracts event triggers and predicts event types. Then we have another component called event argument extraction, which extracts argument and predicts argument roles. And we integrate these components to form this pipeline. So we use pre-trained text generation module, as I said, T5 large, as the backbone of the language model. The input is a natural language sequence consisting of original input passage and prompt, as usual. We design input-output formats with shared common elements across different tasks to enable synergistic joint optimization. All three modules aim to generate subsequence of the input passage. For example, mention identification. To better align the mention identification with ED and EAE, the mention identification extracts all mentions that are candidate event triggers or arguments from the input passage. The input is the passage and the output includes the trigger or argument candidates in the input passage, and we separate it by this separation token. So if there are no mentions, a placeholder is generated. We extract mentions by inputting the entire passage as well as sentence segments selected by a sliding window with a size of few words. For event detection, it extracts event triggers from passage. For a given passage, we construct n sub-event type queries. So this is the cons of LLM. You see, for a given passage, for each query, we input the concatenation of passage in the following prompt segments. And the output of the ED is a concatenation of event trigger text predicted for query's event type, separated by a special token following the prefix event triggers. When there is no valid trigger for query's event type, a special placeholder is generated. Event argument. I remember the word of Jan LeCun that said these language models, large language models, are like print. You don't want to reduce the complexity of your brain to just print function, this print method. Because Jan LeCun, because he knows some neuroscience things, that you have prefrontal cortex, different regions of your brain, so you shouldn't just reduce all of your complex brain components to just a large language model. That's why you have hallucination, you have many things that people don't even talk about. For example, I remember anisotropy problem in pre-trained language model that I explained. Everything is in, of course, that is for not only for large language models, but also for any pre-trained model that has problem. So these transformer architecture, even these transformer architectures are not natural. Transformer architecture is just a special kind of graph neural networks that all nodes are connected. It's a perfect graph. So that's why you have computational complexity problem. So GNN is more natural than transformers. And as I said, you don't need to solve all of your problems in NLP or computer vision to just transformers. And for many reasons that it's just the tip of the iceberg. So contrastive learning for mention boundary perturbation. Understanding the role of mention descriptors and distinguishing the subtle boundary difference are not specially optimized during pre-training or fine-tuning with a text generation objective. We propose to create such a task and train the model specifically to recognize the mention with the correct boundaries from a pool of mentions with similar but shifted boundaries. So we create k-negative instance by perturbing the left and right boundaries of mentions, and so we use cross-entropy loss to learn to generate the correct output given the input. We introduce So for contrastive learning, they use info and CE loss, which I have explained on the playlist for contrastive learning. So we have contrastive learning and then the loss. So you see F1 score for classification and identification of argument. You see F1 score for classification and identification of trigger. Because first you identify your argument, then you classify it. Even for trigger, first you identify trigger, then you classify it. You see state of the art is very low. Even for DICE model, which is the proposed model, all of them are less than 75, or let's say 77.